participate. Is everyone okay to start? Can we start here?
Yep, I'm good.
Okay.
Okay.
Ok, boa tarde a todos. Dando início aqui à defesa de tese de Ryan Vargas Madeira. Boa tarde. Dando início aqui nessa sessão de defesa de tese de Ryan Vargas Madeira, orientado pelo Dr. Thales Sencorte e doutora Leila Maria Garcia Fonseca, cujo título da sua tese é Automatic Land Cover Change Detection, a Deep Learning Based Approach to Map Deforested Area. Nós contamos com essa banca a presença do Dr. Nathan Jacob, da Universidade de Kentucky, Dr. Rogério Galante Neck, da Unesp, Dr. Rafael Duarte Coelho do Centro do INPE, eu, Sidney, e os respectivos orientadores. Eu gostaria de agradecer a presença de todos nesse evento, que é um evento ímpar, um evento um tanto quanto diferente do que a gente está acostumado. I would like to thank Dr. Nathan Jacobs for your presence in this examining bank of the Ryan World. Ryan, você tem entre 30 e 40 minutos, mais ou menos, para a sua apresentação. 40 minutos para a sua apresentação e depois passamos à parte de arguição. Ok? Então, está com você, Ryan.
Ok. Obrigado. Só uma informação pessoal do YouTube, a gente vai transmitir somente a apresentação e depois parar aqui. Eu vou mudar para o inglês agora, porque devido à presença do Dr. Nathan Jacobs, eu vou ter que apresentar em inglês. So, to everyone for watching that, thank you for the committee to accept to participate. And I will present now my PhD work with the title Automating Land Cover Change Mapping, a Deep Learning-Based Approach to Map Deforested Areas. Okay, in the recent years, we have an increased accessibility of remote sensing image. And this large amount of data are a very powerful tool to understand the territory, even for small scales or for large scale areas, especially on national, continental, or even on global scale. And together with this powerful tool, we have an increased the complexity in the analysis for high resolution imagery. We have lots of high frequencies, horizontal layovers and shadows and some distortions due to the off-nadir look angles and another natures of the image. And for medium resolution imagery, we have lower frequencies, lack of well-defined edges, high spectral mixture, and several other types of distortions. And especially an important class of remote sensing application have been the land use and land cover mapping and land use and land cover change detection, because these applications, they provide a powerful tool to understand the territory and to inform and enable public policies. At the same time, it's a challenging task to perform this kind of task for large scale areas, because on manual approach for visual analysis or things like that, we have a large amount of time consuming, it's expensive, and so on. And we also have some important challenge to automate these tasks due to the nature of the image difference between sensors, seasonal effects, cloud shadows, and several other image artifacts that usually they act as a confusing factor for the classifiers. So INPE have been developing since 1988 project that is considered nowadays the most consistent and important temporal series of deforestation maps. It has been developed since 1988 with estimating deforestation rates in the Amazon. And since 2000, digital maps have been made available. And in the last years, a strong effort have been developed to extend these maps to the other Brazilian biomes. And special interest is in the Brazilian Cerrado. That's it's a hotspot of the biodiversity in the country. And especially PRODES maps the anthropic disturbance on primary forests, and together with the TER, it have been playing an important role in the development of public policies to combat the illegal deforestation. And it have been considered the main reference on large-scale deforestation mapping. However, the methodology to develop these maps, it's highly manual nowadays, based on visual analysis of the image, and it's time consuming, it's expensive, and this time consuming doesn't allow to perform, especially for products in a higher resolution, to produce the maps with a higher temporal resolution. So, okay. In recent years, deep learning techniques have raised as a hotspot in the computer vision and pattern recognition communities, and especially the main characteristics of these techniques that make them powerful is their ability to learn abstract representation, important representation from the data. They are not based on hand-designed features. They can have the learning process of the features. It can be optimized together with the classifiers. And okay, given that, the main goal of this thesis is to develop, describe, and assess a fully automatic method based on deep learning to map deforested areas based on Landsat 8 imagery. And we consider the main challenges we had to attack were the large amount of data. If considered the entire Amazon, we have more than 1 terabyte of data. In our case, we developed it for the entire Pará state. We had a data set of approximately 270 gigabytes. And the complexity to generate the trained data set and also to train these classifiers with this large amount of data. So we consider that this thesis has a threefold contribution: a fully automatic method based on deep neural networks to map the forested areas, and 2 spatial temporal variations of the UNet architecture. We consider the first contribution. The second, a platform free and open source to make deep learning techniques available for those analysts without any strong background in computer science. And third, a collection of data sets, of a reference data set for the development of new classification methods that we call PRODES Vision collection of data sets. Okay. Deep learning have been overcoming the state of the art in machine learning tasks. In most machine learning tasks in last years, semantic segmentation, speech recognition, and so on. And the main characteristics is the effectiveness in the representation of the knowledge. When we think about classification problem, we are trying to map the contents of our data to a concept that we imagine to exist there. And this mapping in computer systems, it's done through mathematical functions. And these methods, they were based on our cognitive system, because when we look to the data, we can easily understand things that are not easily representable by mathematical functions, at least not in a direct representation. So as aforementioned, we in the traditional machine learning techniques, we have a lack on efficient representation of the data with hand-designed shallow features, statistics for metrics, and so on. And these features are usually based on hand-designed mathematical functions, and they are not optimizable together with the classifier. When dealing with deep learning, the entire feature extraction process, they are optimized together with the classifier with the same loss function or same set of loss functions. And it makes it's able to represent, to break the function into a set of nested concepts from less abstract concepts like borders or things like that, come to more abstract concepts in deeper layers of the networks. So one special subset of deep learning techniques that have been the most used because of the powerful for image processing are the convolutional neural networks. Basically, these networks, they are based on a set of convolutional operations. A set of filters are applied to the image to extract features. And the weights of these convolutions are the weights of the network neurons. And usually each convolutional block is composed of a convolutional layer, an activation function, and a pooling layer. The activation function, the most used is the rectified linear unit. That is widely used because it's fast trainable, because of that potential for large scale models, large data set, processing large data sets. And it also reduces the vanish gradient problem. And after that, the pooling layers, they are a set of layers responsible to reduce the spatial resolution of the image and representing more abstract data, and also making the receptive field of that layers bigger. And in practical, this means that the network, that layers of the networks will be watching now a wider area in the image. Okay, despite this effectiveness, the convolutional neural networks are not suitable for pixel-wise classification, for semantic segmentation. And in this paper, Long et al. 2015, they proposed a model to transform these networks in an encoder-decoder structure, where they change the fully connected layers. Okay, here, after these sets of convolutional blocks, some fully connected layers are coupled to extract some more features, and then a classifier is coupled that. So they changed these fully connected layers to more convolutional layers, because when mathematically, when you have a fully connected layers where all the neurons from one layer is connected to the layers to the next layer, to the neurons of the next layers, it's similar to a convolution with where the kernel have the same size of the image. So they also added some upsampling, trainable upsampling over these layers in a trainable way through transposed convolutions. And later, some evolutions of that architecture were developed. One of them that have been widely used not only for remote sensing but for medical images and other kinds of images is the UNet. Basically, they couple over the upsampled features. They concatenate the higher resolution features from the previous layers, and then perform more feature extraction layers here to be able to represent more detailed structures of the input image. So, and another important thing is that they use unpadded convolutions. It has the effect of reducing the size of the output image, but at the same time, it allows you to classify very large images because you can break the image in tiles and it will reduce the border effects in the border of these tiles. Some example of applications using the UNet for remote sensing, land use, and land cover mapping are the work of Wagner et al. In 2019 that mapped forest type and disturbance in the Atlantic rainforest, and this other work that extracted roads through residual UNet. Okay, so starting the first contribution of this thesis, we proposed the DeepGeo toolbox. This chapter was based on a paper published on NIGARS 2019. And the basic idea here is that the computational concepts behind deep learning are very complex, and the existing platforms are also very complex for an analyst that have not a strong background in computer science, a strong programming background. So focusing on facilitating the use of deep learning techniques for these analysts without a strong programming background, we proposed this framework that makes available several functions to since the download from the image, to automate them and pre-process the image, train the model, generate data sets, define new models in if you need to extend the platform in a very easy way, and also it allows to quickly automate tasks, classification tasks like that. So the first model is the data catalog, where you are able to download images from the main providers in the world, the main providers that provide free images, ESPA, ESA, INPI for CBERS images, and for some cloud platforms. So basically here is a code example of this model, where in few lines of code, you define the downloader, you query for scenes, plot the results scenes in a dynamic map, query for dates and cloud code, minimum cloud coverage, maximum cloud coverage, sorry. You can generate and place the order and download the image all in an automatic way. So here is an example of the plot of the results of the scene query. You can also visualize some few informations of that scenes here. And here we have a scheme of the integration. I will present here the two next models together because they are strongly integrated, and I will show later some few samples of code. Basically, the preprocessor, you have several functions to compute spectral indexes, generate synthetic bands, standardize and normalize images for the neural network, because usually it's better to work with the image in a range between -1 and 1 to make the training process quicker and have a better performance of the activation function. We have a rasterizer that allows to, given a land use and land cover map, and you can produce the labels for your data set. You can replace labels in cloudy areas with a new class called clouds. You can then produce your data set, generate the slicing chips, shuffle them, and then save these to the disk. Okay, here we have an example of the preprocessing model. I will pass quick through these slides because the idea here is to show how easy it is to define these structures. So you can here define a new index, register this new function in the preprocessor, compute the index, standardize the image, and then save the output in a new raster. And then we have another example of the rasterizer, basically from the line 7 to above, we are defining parameters, and in basically 3 lines of code, given this one is the same, you can rasterize your layer and save it to the disk. So here another example of the dataset generation model, where you have also several different structure to customize your dataset if you need. You can save the metadata together with the dataset for loading in the future if you need, for consulting or keep tracking of your experiments. And you can slice the image in different strategies randomly or sequentially with or without overlap. And then we have the deep learning model that basically have a very optimized data loader based on TF records, and optimized training pipeline also. You can load the preprocessing steps to preprocess the image you need to classify after the network's trained, load the weights of the trained network, and then perform your classification. This platform was mainly developed on over TensorFlow, NumPy, GDAL, and scikit-learn. TensorFlow is responsible for the deep learning part. Okay, so here is a very simple example of how to define and train a deep neural network. In this example, we are training an FCN8S proposed by Long's paper. And if you need to perform data augmentation or any regularization strategy because of the to avoid overfitting, you can just define what operations of data augmentations you want and define the parameters of the regularization strategy. Or you can also define new neural network and register in the same way like we register here in the preprocessing model. Okay, and late we have a visualization and classification analysis model where you have already several statistical metrics. You just call one simple function and you have a complete report of your classification, the quality of your classification. And you have also several visualization tools. Okay, coming now to the second contribution of this thesis, we have PRODIS vision collection of data sets. We enumerate here the main challenge in our understanding. First of all, how to process this such a large amount of data that goes from hundreds of gigabytes to more than 1 or 2 terabytes. If you come only for the Amazon biome, we would have more than 1 terabyte of data for one single training data set. For the Cerrado biome, around the half of that. And this considering only 4 or 5 years of data. So deal also with some temporal issues on ground truth, cloud coverage, and things like that. And when it comes to PRODIS data, for example, once the purpose is to produce one deforestation map for the year, several images from different dates are used to detect the deforested areas. And usually the main goal is also to map only the disturbance on primary forests. So once an area is mapped as deforestation, it will not be looked again, because even if it regenerates and becomes secondary forest, it will keep in the map as deforestation to keep the consistency of the temporal series, and because that's not a primary forest anymore. But I will show later how this could, in terms of training a neural network, this generates some few problems. And also another problem is the cloud coverage, especially in the Amazon region, where most regions are covered by clouds the entire year. It's hard to find a cloud-free image in the entire year. So we propose here also a methodology to generate new reference data sets. And basically, it's based here on what we developed for Project Vision dataset with Landsat 8 image, but it can be easily applied for several different types of images. Basically, we normalize the data. If it's multi-temporal, stack pairs or even tuples of data, crop the patches, rasterize the labels, insert cloud labels to replace areas of interest that are under clouds in the image being classified. You can replace that with a new class representing the clouds, and then perform all the process to shuffle, split, and then save the TF records of the data set. Here is an example of how we organized the classes in the data. Basically, prods have 5 main classes: the deforestation, forest, non-forest, that are composed of different types of vegetation that are not classified as a forest in that region. So, and also hydrography, and areas that are not observed during the entire year. They are considered as forest, but they are kept as not observed to in the maps. So we just grouped these classes, these 4 classes in the class not deforestation, and then using the Landsat quality assessment data, we replaced the areas under clouds with the label of the clouds to train our network to detect where there are clouds in that image, and then say, okay, we cannot observe that area because this is a cloud. Here is a quick show of how the TF records are structured, with one field for image labels and 4 describing features to be able to decode that in the data loader. And here is we generated three configurations of this data set. And for next versions, we aim to also develop new versions with higher scale areas and other different regions also. So this first configuration was developed for development purposes, because when you are developing a neural network, it's good to have a smaller data set to perform the iterations quicker, train the network, adjust the parameters, train it again, adjust the architecture if you need, and so on. Here we have the spatial distribution of the patches over the image, and this configuration as the next one. It was generated with a 5 years time series from 2013 to 2017. And in our experience, we used the year of 2018 to perform the classification and evaluation of the algorithms. Here is the second configuration of the data set that was developed for testing the applications for large scale areas. We have here the entire state of Pará, and it comprises around 1.25 square kilometers of area. And so as I will show later, this generates a really huge amount of data, around 273 gigabytes. And the third configuration was developed in the Brazilian Cerrado to be able to test the application of the developed method for different regions. Here, it's a first version for the Cerrado. For next versions, we aim to produce data sets for the entire biome as well as for the Amazon. So here we have a summary of the data sets. First two configurations, they were developed in a single temporal configuration and in a multi-temporal configuration, and the second and third only in a multi-temporal configuration. So here the number of training, test, and validation patches, and the size in gigabytes. So we can see here that even the smaller ones, they represent a really huge amount of data, around 25 to 27 gigabytes. And here we have what we consider to be the main contribution of this thesis, that is a spatial temporal approach to map deforestation in Amazon and other biomes, as we will show in other results. And this part was based on a paper accepted for the Geoscience and Remote Sensing letters, and it is in publication phase. Probably next weeks or next month, it will be available online. And an overview of the methodology of the paper here. Basically, here's a simplified version of the methodology to generate the data set together with the training phase. We generate the data sets here, train the UNet, validate the results, and save the weights to perform classifications over new images later. Okay, and we also proposed in this paper two spatial temporal variations of the UNet based on a concept that we call a trainable temporal fusion. When we are dealing with mapping land use and land cover chains, most of the time only the spatial context is not enough, and you need at least a short-term temporal context to be able to understand what's changing in the territory. So here in this concept, we basically concatenate the two images and perform one-by-one convolution with a trainable filter that will be optimized together with the entire network with the same loss function. In this first, the early fusion UNet, we perform the temporal fusion before the encoder of the network. The second architecture is a little bit more complex. We propose the concept of a late fusion UNet, where we duplicate the encoder of the network here. And for each feature extraction layer, we perform the temporal fusion, concatenating the feature maps resultant, and then performing the one-by-one convolution before bringing them to the decoder. In this case, it demonstrated to be a little bit more powerful, but computationally much more expensive due to the large amount of data generated in these feature extractors. Here, some experimental results for the smaller area, the first data set. In these experimental results, we got an accuracy of approximately 95%. And I will show a little bit more of these metrics now. We compared here the baseline UNet, that is the traditional UNet architecture, with the early fusion and late fusion UNet, with two different losses, the weighted cross entropy and the average soft dice. These two different losses, they have the characteristics of being a little bit more invariant to unbalanced data. So they compensate unbalanced data with some weights or some another mechanisms. And here in an average matrix, the late fusion UNet performed a little bit slightly better than the previous two architectures, with an average accuracy of 94.7%, F1 score 9.947, and a very high AUC metric also. But for some few cases, when you compare in a class-wise way, when we compare class by class, the baseline or the early fusion UNet, especially with the soft dice, they performed better, especially in the precision. And this case of the precision might be explained because in the case of the soft dice, because the soft dice is a metric of overlapping, and while the weighted cross entropy, it uses another weighted strategy, but so it reduces, it increases the weighted cross entropy, increases the overall accuracy, but has at the same time more false positives. And in the case of soft dice, you have less false positives because of that. You have a higher precision for some cases, but you have a smaller over accuracy. Here, I will show you why the problem of the regeneration becomes a problem when training a neural network like that. In this case, once we use the entire deforested area to train the network and also to classify later, we had some few areas like this one rounded in red here, that this area was deforested in 2007 and regenerated. So when it became secondary forest, but when you look for the image, the appearance is very similar to the behavior of the primary forest, making the network to don't classify that as deforestation. But we consider that due to these areas, this kind of characteristics, that's not an error of products, but it's the methodology that was developed. Due to that, we consider that our error was a little bit overestimated, because this part we can easily fix in a final map with a mask, using the mask of the previous years or things like that. And we have here also some, in the ground truth, we have some false positives for clouds due to because the Landsat quality assessment data is generated in an automatic way. So it has an intrinsic error. And we can see that our network was also robust to this kind of error, classifying only the clouds that really exist in the image, like in the bottom right corner, here in the cyan circle, and areas like that. So scaling up for large scale areas, we classified the entire Pará state. As aforementioned, it's a very huge data set, and it was very challenging to optimize the model, to adapt the model to perform a classification in so huge area, especially in the training process that have a data set with 270 gigabytes, but also for the classification process, not because of the network, because of the pre-processing steps. We have here, for each year, we have a mosaic of around 50 gigabytes. So to slice it in smaller patches and all the process is a challenging process without a very good machine. Okay, some results here. We got an overall accuracy of almost 94%, 93.89%, and an F1 score of 92.63. Here, we can also, only one thing first, in this experiment, Once the weighted cross entropy performed a little bit better with the late fusion UNet, due to the computational resources, we only performed the test with the late fusion UNet and the weighted cross entropy. We performed also some tests with the average soft dice, but for this kind of large scale mapping, it demonstrated to be very unstable and hard to train. So because of that, we didn't include these results in the thesis. So we can observe here, especially in the confusion matrix, that we have also a considerably high rate of false positives. We believe that it comes from the reasons I showed before, from the false positives in the ground truth, and also another here, when we scale up, we have more confusing areas, like if we consider the non-forest class of products that in the two images below is shown as a magenta here, we can see several several false positives they happened inside the area of these classes of this class. So we can also believe that this could be also easily solved with a mask. So we consider also that this is an overrated error that can be easily reduced with some post-processing steps. And here, a generalization for the Brazilian Cerrado. We selected this area. This area is an area around the Corentina County in Bahia state. It's in the border between Bahia, Tocantins, and Minas Gerais. Okay. And we have chosen this area because it's also a deforestation hotspot in the biome. Here, a general overview of the results. We achieved here an accuracy always over 9%, but we got also a higher false positives rate, 9% with weighted cross entropy and 5% with the average soft dice. We believe that here this is also because of the type of vegetation we can find in the Cerrado. Now, some conclusions. We presented three main contributions: a fully automatic method to map the forested areas, a framework to make deep learning available for analysts without a strong programming background, and a collection of reference data set that we believe can guide the development of new methods for land use and land cover mapping. And some more conclusions here. DeepGL demonstrated to have a good potential through the presented experiments, being very easy to use and demonstrating potential to automate the tasks. And as future works, we aim to extend it to another application and domains of remote sensing, extend it with new types of network, like recurrent neural network for dense time series analysis. And for prod vision data sets that also demonstrated a good potential to guide the development of methods based on convolutional neural networks. And also as future works, we aim to scale up for the entire Amazon and Cerrado biomes that would accomplish an area of approximately 6.23 square kilometers, and optimize the data partitioning to have a more efficient storage, and also to make the data loading a little bit more efficient. Generate new versions with different class configurations, different areas, improve the cloud masks to reduce the false positives, and include images from different sensors like Sentinel and Seabird collections to to allow the development of multi-sensor classifiers. And for the classification methodology, we consider to be very effective, having potential to be used in the future to automate or semi-automate projects like PRODES, Cerrado, and other mapping projects. It was robust for noises in training data. We got high accuracies for all tested areas. It demonstrated to be scalable for large-scale areas and effective to be applied to different biomes. And for future works, we consider that maybe trying to include the masks as a previous knowledge to the models could be a good improvement. Considering auxiliary data like topography, roads, or things like that, and generalize the method to work with multiple sensors also, improving then the temporal resolution of the maps being produced. And also, we aim to be able to improve the time component, allowing deeper time series, but also keeping the method scalable for such large areas. So thank you, everyone. I would like to ask some excuse to Dr. Jacobs to say some words in Portuguese to acknowledge some people. And also, first of all, I would like to thanks to Dr. Jacobs to the supervision in part of this work. He received me in the University of Kentucky in a very good way and gave some very good contributions to this work. So thank you very much. I will switch now to Portuguese to small thanks. Bom, eu gostaria de agradecer todo mundo que participou do trabalho, todo mundo que participou da minha vida nesse processo. Quem estava perto sabe como que foi. E agradecer principalmente a confiança dos meus orientadores. Obrigado a todos. Bom, só despedir, a gente vai se despedir agora do pessoal do YouTube. Eu vou parar a transmissão aqui para as discussões com a banca.